Okay, so we are looking at, this is question 36 from the Trigonometry Final Exam Review. We're being asked to transform the polar equation to a rectangular equation in rectangular coordinates and then to identify and graph the equation. Okay, so the first thing we want to do is let's write the equations that we know. We know x is equal to r cosine theta. We know y is equal to r sine theta, and we know r squared is equal to x squared plus y squared. And so looking at our polar equation, I realized that I really would like for this r to be r squared, and that way I can rewrite it as x squared plus y squared. And I noticed that for the sine, it really needs this r in front. So I need an r on both sides of the equation. So what I'm going to do to make that happen is I'm going to multiply both sides of the equation by r. So over here we have r times r would give us r squared, and then on this side we have 6 times r would be 6r sine theta. All right, so now we can rewrite the r squared as x squared plus y squared. And then we can rewrite this r sine theta as y. So I've got equals 6y. Now, I recognize this as a conic, but I would like to go ahead and write it in a little bit better format so I can recognize it better and graph it more easily. So what I'm going to do is actually take this equation, and I'm going to go ahead and get my like variables on the same side. So I'm going to subtract the 6y from both sides. And then I'm going to complete the square on this y squared minus 6y so I can turn it into a perfect square trinomial. So in order to complete the square, remember that you need to check and make sure that the coefficient in front of the squared variable is a 1, and it is in our case. Then you want to take the coefficient in front of the y to the first, and to complete the square, we're going to take that divided by 2 and then square it. So we'd have -3 quantity squared, which is 9. And so I'm going to rewrite this as x squared plus y squared minus 6y. I'm going to add on the 9 here to turn this into a perfect square trinomial. And then on the other side I have 0, and then because I added 9 onto the left side of the equation, I have to add 9 to the right side of the equation as well. So I still have my x squared. I'm going to factor this perfect square trinomial, and a shortcut that you can use is you can take your coefficient in front of your y and look at it as after you divided it by 2 in its most simplified form right before you squared it, and that will tell you how this will factor. So I know this -3 will match up here. And you can always double check it. You can go off to the side and write y minus 3 times y minus 3, and if you FOIL that out, you will get y squared minus 6y plus 9. Then over here on the right side, I still have a 9. Now I do recognize this now as a circle. We know the standard form for a circle from pre-calculus is x minus h quantity squared plus y minus k quantity squared is equal to r squared. So we're going to write our equation in that format. So I could write it as x minus 0 quantity squared, because that's the same thing as x squared, plus y minus 3 quantity squared, and then we know 9 is really 3 squared. And when you have your standard form here, you know that the center of your circle is at HK, and you know the radius is r. So in our case, the center is at 0, 3, and we know our radius is also 3. Now I can easily graph this now that I know that I have a circle in the rectangular plane. What I'm going to do is go ahead and put the center of the circle in first at 1, 2, 3, so 0, 3 would be right here. And then to graph a circle, you're going to go up whatever your distance of your radius is. So 1, 2, 3, that will give me another point. I'm going to go from my center to the right 3, so that's going to give me another point here. To the left 3, and then from the center down 3. and then I can graph my circle. I do, however, want to go ahead and graph this in its original polar form. You don't have to convert over to a rectangular equation to be able to graph it. So let's look at our original was r is equal to 6 times the sine of theta. And I'm going to switch over to a polar grid here. And what I'm going to do is just plot some points. And I'm going to use those polar coordinates to go ahead and then graph that same circle that we just graphed, but without having to do the conversion. So what I'll do is I'll pick some theta values and then calculate my r. I want to use things that are easy for me to work with, things that I know from my unit circle or from my two main triangles. So I'm going to start at 0 radians, so I'll plug in 0 for theta. So we have r is equal to 6 times the sine of 0. Of course, I'm very familiar with 0 radians. We know on the unit circle that we're looking at the point 1, 0. And we know we always associate sine with the y-coordinate. So we know that sine of 0 would be 0. So we have 6 times 0, which is 0. So that gives me the first polar coordinate of 0, 0. So we're at 0. But then with an r of 0, we didn't go anywhere. So we're right here at the pole. Now, moving on, you can pick anything you want in quadrant 1 that's easy for you to work with. You could use pi 6 or pi thirds, but I'm just going to go halfway here and use pi fourths. So I will plug in pi fourths. So we're looking at r is equal to 6 times the sine of pi fourths. We know, of course, that we're looking at a reference angle of 45 degrees, and we can see that pi fourths is in quadrant 1. So we know in quadrant 1 all our trig functions are positive, and I know at 45 degrees we're looking at root 2 over 2. Or if you like to use your right triangles, that's fine too. So you can use your 45, 45. This is 1, 1 squared to 2, and combine that with your SOHCAHTOA. And of course we know sine, if I use this as the reference angle, is opposite over hypotenuse. So we have 1 over root 2. Then if you rationalize that by multiplying the numerator and the denominator by square root of 2, you'd get root 2 over 2. Either way is fine. And again, because we're in quadrant 1, it would be positive. So either know your points on the unit circle or use your right triangle. Okay, so then seeing what I have, I'm going to go ahead and think of that as over 1. I see that the 2 will reduce this to a 3. And I'm left with 3 squared root of 2. For graphing purposes, I'm going to go ahead and use my simple calculator to approximate that. Looks like it's about 4.24. So I'm going to plot that point next. Well, let me actually do the graph in purple. So let me mark my original point at the pole here. And then I want to do pi fourths, and then my r is 4.24. So let's see, 1, 2, 3, 4 circles out, and then a hair more would be about here. So far, this is what I have. Okay, the next thing that looks pretty easy for me to plot, let me get a little closer here, would be pi halves, which we know is right here. And so I'm going to plug that into my equation. So we'd have r is equal to 6 times the sine of pi over 2. Again, from our unit circle, we know at pi over 2, we're looking at the point 0, 1. And we know that, of course, sine would be the y-coordinate, which is 1. So we have 6 times 1, which is 6. So at pi halves, my r is 6. So I'm going to count 6 circles out. 1, 2, 3, 4, 5, 6. So let's see, that's going to be about here. And so I'm going to go ahead and connect those two, moving this way, trying to make it look a little bit better. And you could pick some more points as well. Okay, and then just keeping with my pi fourths theme, since that's what I chose, I'm going to use 45 over here in quadrant 2. which we know is 3 pi over 4. And so I'm going to plug that in for my theta. So I have 6 times the sine of 3 pi over 4. Again, the reference angle is 45, and we can see we're in quadrant 2. We know from our triangle earlier, or from our points on the unit circle, that's root 2 over 2. And then using our all students take calculus, we see that sine is positive, so we're going to keep it as positive root 2 over 2. Think of this as over 1. I'm going to go ahead and reduce the 2. We'll reduce the 6 to 3. So again, we're looking at 3 squared to 2. And I'm going to approximate that at about 4.24. So now we're looking at this point. So at 3 pi 4, so I'm going to count out 1, let's see, 1, 2, 3, 4.24 would be about here. So I'm going to connect that. And then last, just to complete it, I can see another easy theta for me to pick would be pi. So that's going to be the next thing I plug into my equation. I'd have 6 times the sine of pi. And of course, right here at pi, we know that point on the unit circle is -1, 0. But again, we associate sine with the y-coordinate. So we're looking at 6 times 0, which is 0. And so now I'm going to be right back at the pole because we're looking at pi, which is right here. And then 0 means our r is 0, so I'm counting 0 circles out. And so I would connect my circle. So we still get the circle. I'm going to clean it up a little bit here, make it look a little bit better. So we're still able to do that and plot it simply by picking points or picking thetas that are pretty easy for us to work with and then just plotting them, and then we can generate our circle that way.